How likely is it that it rains tomorrow? That you win the lottery? That a medical test is accurate? These are all questions about probability, our way of quantifying uncertainty. Probability is a number between 0 and 1. 0 means impossible, 1 means certain, and anything in between reflects how likely something is to happen. For example, flipping a fair coin gives you a probability of 0.5 for heads. Rolling a 6 on a fair die, that's 1 out of 6, or about 0.167. But here's the key. Probability is always based on a model. When we say there's a 70% chance of rain tomorrow, that number depends on weather models, historical data, and how we define rain. So probability isn't just about the event, it's about the event plus the information we have. Let's break it down. First, we need to understand the building blocks. A random experiment is any process with an uncertain outcome. Flipping a coin, drawing a card, checking whether a customer makes a purchase. Each of these has a sample space, the set of all possible outcomes. For a coin, that's heads or tails. For a die, it's the numbers 1 through 6. An event is any subset of that sample space. So if you roll a die, the event even number includes 2, 4, and 6. Now, how do we assign probabilities to these events? That's where the formal definition comes in. Probability is a function, p, that assigns a number to each event, and it must follow 3 rules. First, non-negativity, probabilities can't be negative. Second, normalization, the probability of the entire sample space is 1. Third, additivity. If 2 events can't both happen, the probability of either happening is the sum of their individual probabilities. These 3 rules, non-negativity, normalization, and additivity, are the foundation of all probability theory. So, how do we actually calculate probability? There are 3 main approaches. First, classical probability. This is used when all outcomes are equally likely. The formula is simple. The number of favorable outcomes divided by the total number of outcomes. For example, the probability of drawing an ace from a standard deck is 4 out of 52, or about 0.077. The probability of rolling an even number on a die? 3 out of 6, or 0.5. Second, empirical probability. This is based on data. If you flip a coin 1,000 times and get heads 480 times, the empirical probability of heads is 480 divided by 1,000, or 0.48. The more trials you run, the closer this gets to the true probability. That's the law of large numbers. As the number of trials increases, the relative frequency stabilizes. Third, subjective probability. This is used when you can't repeat the experiment. What's the chance a new product succeeds, or that a patient recovers from a rare disease? These are one-time events. Here, probability reflects a degree of belief based on expert knowledge and prior data. This is the foundation of Bayesian probability, which we'll come back to. Now let's talk about the core rules that help us calculate probabilities in more complex situations. First, the complement rule. The probability that an event does not happen is 1 minus the probability that it does happen. For example, the probability of getting at least 1 6 in 4 rolls of a die is 1 minus the probability of getting no 6s. That's 1 minus 5/6 to the 4th power. Second, the addition rule. If you want the probability of A or B happening, you add their probabilities and subtract the overlap. So P of A or B equals P of A plus P of B minus P of A and B. For example, the probability of drawing a heart or an ace from a deck is 13 out of 52 plus 4 out of 52 minus 1 out of 52, which equals 16 out of 52. Third, conditional probability. This is the probability of A given B has occurred. The formula is P of A given B equals P of A and B divided by P of B. For example, if you know a card is a face card, what's the probability it's a king? There are 12 face cards and 4 of them are kings, so the answer is 4 divided by 12, or 1/3. Fourth, the multiplication rule. The probability of A and B both happening is P of A times P of B given A. For example, what's the probability of drawing 2 aces in a row without replacement? First draw, 4 out of 52. Second draw, 3 out of 51. Multiply them to get the answer. Fifth, independence. Two events are independent if the occurrence of one doesn't affect the other. For independent events, P of A and B equals P of A times P of B. For example, flipping two coins, the probability of getting heads on both is 0.5 times 0.5, which is 0.25. But be careful, mutually exclusive events are not independent. If A and B can't both happen, knowing that A happened tells you B didn't. Now let's talk about Bayes' theorem. This is how we update probabilities when we get new information. The formula is P of A given B equals P of B given A times P of A divided by P of B. Let's say a disease affects 1% of the population. A test has 99% sensitivity and a 5% false positive rate. If someone tests positive, what's the chance they actually have the disease? Bayes' theorem helps us calculate that. It turns out, even with a positive test, the probability of having the disease might be much lower than you think, because the disease is rare and false positives are common. Next, random variables. These are variables that assign numbers to outcomes. For example, X could be the number of heads in 10 coin flips. Random variables can be discrete or continuous. Discrete variables take countable values like 0, 1, 2. Continuous variables take any value in a range like height or time. For discrete variables, we use a probability mass function. For continuous variables, we use a probability density function. And here's a key fact. For continuous variables, the probability of any exact value is 0. Only intervals have positive probability. One of the most important continuous distributions is the normal distribution, the bell curve. It's symmetric, centered at the mean, and used to model things like test scores, heights, and measurement errors. We often use z-scores to standardize values and find probabilities using normal tables or software. Now, how do we actually calculate probability? First, we can use counting methods like permutations and combinations for situations with equally likely outcomes. Second, we apply the rules we discussed, complement, addition, multiplication, and conditional probability. Fourth, we use known distributions like binomial, Poisson, or normal when the situation matches their assumptions. Fifth, we can estimate probabilities from data using relative frequencies or statistical models. And finally, we can simulate the process using Monte Carlo methods. This is especially useful when the math is too complex to do by hand. So, to sum up, probability is how we quantify uncertainty. It's calculated using models, data, and logical rules. There are different approaches, classical, empirical, and subjective, and each is useful in different situations. We use core rules like complement, addition, multiplication, and conditional probability to build more complex calculations. And when things get tricky, we turn to distributions or simulations. Probability isn't just a math topic, it's a way of thinking. It helps us make better decisions, interpret data, and understand the world around us.